Welcome to the class. In the video titled The Synthesis of Oximes from Aldehydes and Ketones, we have learned how to convert a ketone to a ketoxy. In this video, we intend to learn the conversion of a ketoxime to an N-substituted amide. So how do we convert a ketoxime to an N-substituted amide? There is a very simple way to do it. The way to do it is to treat the ketoxime with a mineral acid. So when we treat the ketoxime with a mineral acid, what we get is an N-substituted amide. The reaction, which is called as the Beckmann Rearrangement reaction. So what happens in a Beckmann Rearrangement reaction? It is seen that the H plus from an H2SO4 is dissociated. The dissociated H plus attacks the lone pair of electron on the oxygen. When it attacks the lone pair of electron on the oxygen develops a positive charge. Now what follows is a series of electron pair transfer within the molecule. Consequent to it, one of the alkyl group migrates from the carbon of the oxime to the nitrogen of the oxy. The more electron donating group is what migrates to the nitrogen of the oxy. And this reduction and rearrangement of the alkyl group to the nitrogen of the oxime is what leads to this product, which is N-substituted amide. So what is Beckmann rearrangement? Beckmann rearrangement is an acid catalyzed reduction and intramolecular rearrangement of an ketoxime to a N-substituted amide. Beckmann rearrangement is also used in the conversion of an aldoxime to nitrile compounds and the conversion of cyclic oxime to cyclic amide, which are otherwise also called as lactams. However, in this section, we are going to focus our attention on the conversion of ketoxime to N-substituted amide. We'll better understand this reaction by looking at its mechanism. Let us now look at the mechanism of Beckmann rearrangement. This is the ketoxime and this is the N-substituted amide. So what is there in the end product here is that it is an N-substituted amide. Here you are seeing that a hydroxyl group is attached. So we need to remove this hydroxyl group, but it is very difficult to remove this oxygen. You know why? Because the oxygen has a two lone pair of electron. That makes the oxygen sufficiently electron rich. And because oxygen is sufficiently electron rich, it is a very good nucleophile. It is a very good nucleophile. It is attracted to the nucleus of the nitrogen atom because it has got excessive electrons. It won't leave. Therefore, it is a very poor leaving group, very poor leaving group. So what we intend to do is to reduce the electron density on the oxygen atom. For that purpose, we use a mineral acid. So when we use a mineral acid, NH plus dissociates from the mineral acid. It attacks the lone pair of electron on oxygen. When it attacks the lone pair of electron on oxygen, there is scarcity of electron on oxygen now. Because of this, oxygen develops a positive charge. When oxygen develops a positive charge, it becomes a very poor nucleophile and a very good leaving group. Because now the nucleus of oxygen is not attracted to the nucleus of nitrogen. And the second thing here is that when oxygen develops a positive charge, oxygen is already electronegative. A positively charged oxygen atom will be more electronegative than ever. So what happens is that neither the oxygen is attracted to the nucleus of nitrogen. On the top of it, the oxygen is positive and it tries to take the electron pair that it shares with the nitrogen. So this pair now goes to H2O plus and that leads to elimination of H2O. that is water. When this electron pair is taken away by this, the nitrogen develops a positive charge. Now look at the nitrogen. If it develops a positive charge, what would happen? Nitrogen is electronegative. A positively charged nitrogen atom would be more electronegative. In that case, the nitrogen would attract the adjacent electron pair. And there are two options with the nitrogen. Either it can attract the electron pair from this alkyl group, or it can attract the electron pair from this alkyl group. Which one does nitrogen choose? It will definitely choose the more electron donating alkyl group. Suppose this is the more electron donating alkyl group, R dash. That would mean that it would pump the electron pair more towards nitrogen, and nitrogen will definitely take that electron pair which is more pumped. So when that happens, when this pair goes here, the R dash becomes positive in charge. Now R dash doesn't have any other option rather than to attack the electron, the lone pair of electron on the nitrogen atom. So what results is a nitrilium ion. You can see the triple bond is formed between carbon and nitrogen, and the R dash consumes the lone pair of electron which was on the nitrogen atom, because of which the nitrogen became positive. This, dear students, is called as a nitrilium ion. This is a nitrile, C triple bond N, and this is an alkylated nitrile. So an alkylated nitrile is called as a nitrilium ion. A nitrilium ion is quite unstable because the nitrogen is very much electronegative here. So what this positively charged nitrogen does is to take this electron pair which it shares with the carbon. When it takes this electron pair which it shares with the carbon, the loss is with this carbon. It loses one electron. So what would happen? This carbon would become positive. Dear students, both these structures are now interconvertible. That means if a reagent consumes this, more of this will convert into it, and vice versa. Now you know the water, it was eliminated here. It again comes into play. Water is amphiprotic in nature. What is the meaning of amphiprotic? It can act as a base when it encounters an acid, and it can act as an acid when it encounters a base. Here it is encountering a very strong Lewis acid, this one. So it behaves like a very strong Lewis base. It donates its electron, lone pair of electron, to the positively charged carbon. So the carbon's positive charge evades away. But in the process of doing so, because oxygen lost its lone pair of electron, the oxygen gets a positive charge. Now the oxygen, you know, it's electronegative, and its electronegativity further escalates because of the positive charge here. So it tries to take the electron pair which it shared with one of the hydrogen atom. Now this leads to elimination of a proton and the restoration of electron pair back on oxygen. The restoration of electron pair back on oxygen, like this. Now this, dear students, is enol form. Enol form. Now what can happen is that this hydrogen, it can get attracted to the lone pair of electron on the nitrogen atom. I will tell you why it got attracted to the lone pair of electron on nitrogen atom. So it gets attracted to the lone pair of electron on nitrogen atom. When it does so, nitrogen atom becomes positive here. The positively charged nitrogen atom pulls this electron pair towards it. When it pulls, the positive charge goes away. But however, because this carbon lost its one electron, this carbon gets a positive charge. This positively charged carbon atom now can attract the electron pair that is on oxygen, the electron pair that was formed when H plus went to nitrogen. That electron pair, not the lone pairs. the electron pair which the hydrogen left, that can be attracted here, and the result is a keto form. The keto form is nothing but N substituted amide. That is what the product is, the N substituted amide. Now the success is that the keto form is 76% in proportion and the enol form is 24%. They do interconvert at room temperature. They are tautomers. Tautomers are functional isomers. They have same molecular formula. They are functional isomers that do interconvert among each other. And the interconversion is more towards the keto side. That is the success of the Beckmann rearrangement. And as you consume more and more of ketone, enol converts more and more to the keto side, leading to more and more formation of N substituted amide. The reason why keto is more in proportion compared to enol is because more energy is released in the formation of carbon-oxygen double bond compared to the carbon hydroxyl single bond. When more energy is released, that would mean that the keto form is thermodynamically more stable. So its formation is much favored. So what we get here now is the N substituted amide. We will look at one of the examples of Beckmann rearrangement now. Let us now look at one of the examples of Beckmann rearrangement. For this purpose, I have started with acetophenol. I treat it with hydroxylamine in the presence of an acid. And what I get is a methyl phenyl ketoxime. This reaction involves the acid catalyzed nucleophilic addition of hydroxylamine to acetophenone with the elimination of a molecule of water. We have discussed already this reaction in the synthesis in the video titled The Synthesis of Oximes from Aldehydes and Ketones. Please note that this is not the Beckmann rearrangement reaction. This one is the Beckmann rearrangement reaction. In the Beckmann rearrangement reaction, we convert a ketoxime to an N substituted amide. So how do we convert it? We take this methyl phenyl ketoxime and subject it to treatment with a mineral acid. So what happens when we use a mineral acid? An H plus dissociates from the mineral acid. That H plus, it goes and takes the lone pair of electron on the oxygen. The oxygen becomes positively charged, and what follows is a electron pair transfer within the molecule. This is followed by the migration of one of these groups to the nitrogen. Now which groups migrate to nitrogen? Definitely the more electron donating one, it goes to the nitrogen of the oxy. Among these two, this is the more electron donating one, this phenyl one. So it migrates to the nitrogen of the oxy, and what results is an N-phenyl acetamide. So therefore, what I said in the beginning of the class, I say it now too. The Beckmann rearrangement is an acid catalyzed first reduction and second rearrangement of the ketoxime to N substituted amide. Dear students, I hope you have understood and I hope you have liked the class. If you have done so, please do not forget to like, share and subscribe this channel. Thank you very much.